In one of his seminal papers, published in 1956 in the Quarterly Journal of Economics, Robert Solow shows in 3 steps how to derive what we know these days as the fundamental equation of the Solow model. In this video, I will quickly explain how to derive it using a different approach. And this is because Solow uses continuous time, but in many cases in economics, we explain the Solow model, but using discrete time. So I will be deriving this fundamental equation using discrete time, which requires extra steps, unlike the easy way to do it using the continuous times and derivatives, right? So that will be way easier, but probably you will get a better intuition after this explanation using discrete time. All right, well, everything starts when we consider first what we know as the dynamics of the model. And the dynamics of the model suggests that aggregate capital stock will be accumulated according to the following equation. What we will say is that aggregate capital stock in the next period, so note that I'm using uppercase K when I refer to aggregate capital stock. The subscript refers to the period of time that we are referring to. In this case, I'm saying capital stock in the next period will be determined by what I decided to invest in this period, plus the part of the capital that didn't depreciate in this period. So what I have in parentheses is 1 minus delta, where delta is the depreciation rate. And uppercase I refers to investment. So one of the first things that I will do from this expression is to distribute the product. I will be doing everything step by step. Obviously, if you want to, you could skip some steps. That's not a big deal, but let's say we'll be writing all the mathematical steps. So first thing that I will do is to subtract on both sides of this equality, KT. So clearly what we have on the left-hand side is the difference in capital stock, and on the right-hand side, I get rid of this KT. So I'm gonna rewrite it. As I said, the left-hand side is just delta KT plus 1. And on the right-hand side, the only thing that I have left is investment minus delta KT. And this is probably the most, like the initial and easy step. We just re-express the dynamics of the model by saying how capital stock changes over time. From here, the trick is to replace the value of delta KT plus 1 for an approximation. Now, actually, one of the things that I will show you in this video is that the fundamental equation of the Solow model in discrete time is not an equality, it's just an approximation. So if you allow me to go back, properly speaking, with discrete time, this should be just an approximation. Now, the approximation comes from the step that I'm about to explain. Let me open a quick parenthesis here to explain that step. I will write it on this part. And the parenthesis is the following. We're going to use one of the properties of growth rates. And in particular, there is a property that suggests that you could approximate the growth rate of a ratio as the difference of the elements the difference of the growth rates of the elements of the ratio. In particular, suppose that you have a ratio like x divided by y, no? And you would like to compute the growth rate of this ratio. The approximation suggests that this growth rate will be something like the growth rate of, the variable in the numerator minus the growth rate of the variable in the denominator. So we will use this property, but in the context of the Solow model. The ratio that we have is the capital labor ratio. Capital labor ratio, if you remember, I'm just going to put it here in green, is this ratio. I'm using N when I refer to labor. It seems a little bit unconventional, but that's one of the things that I decided to do in one of my courses because I don't want the students to get confused with the lag operator. So assuming that N refers to labor, this ratio gives you what is known in the literature as the capital labor ratio, which is simplified by the lowercase k. So using this notation, what I will say is we are interested in the growth rate of this ratio, which is no other thing than the capital labor ratio. And according to the property of the growth rates, we're going to say that the growth rate of this capital labor ratio should be approximately the same as the growth rate of capital stock in aggregate levels minus the growth rate of population or labor, right? So one of the things that we're assuming in this model is that everyone in the economy works. So that's why I'm using distinctively population and labor, right? And the other thing that you most likely learn in your courses is that according to the Solow model, we assume that population grows at the rate n. In other words, if from this expression you solve for delta kt plus 1, but I'm referring to the aggregate change, then you will have an expression that looks like this. In fact, let me, as I said before, write all the steps because I don't want you to get any kind of confusion. So the first thing that I will do is to multiply by kt on both sides of the equality. So easy step, it will be just kt on the left-hand side, delta kt plus 1 over kt. And this is approx delta kt plus 1. Remember, the moment I multiply by kt, I just got rid of the kt that I had in the numerator. Minus, we know that delta nt plus 1 over nt is just lowercase n multiplied by kt. And the final step for me right now is to add on both sides of the equality and kt. That's the only thing that I'm going to do. And I'm going to rearrange. So my new variable on the left-hand side will be the change in the aggregate capital stock. And we said this is approximately the same as aggregate capital stock multiplied by the growth rate of capital stock per worker minus nkt. And this is precisely the expression that I would like to use in the dynamics of the Solow model, right? Because what we have here is delta kt plus 1, which is exactly the same as this delta kt plus 1 that we have here. I will replace it. If you want to see in particular where did it come from, just copy this expression and do it yourselves. But the only thing that I will do is to use the expression that I have at the end in this blue square instead of the delta kt plus 1 that I have in the dynamics of the model. And just to be a little bit more didactic or clear with this explanation, I will replace it in blue, okay? So what we said is that delta kt plus 1 is kt times the growth rate of capital stock per worker minus n kt. Let me just quickly go back to verify that this is exactly what we had. Oh, by the way, I just realized that I had a mistake because the step that I did on the left-hand side was to subtract by, sorry, nkt, right? Which means that the moment I add nkt on the left-hand side, this should be positive. Sorry, that was my bad. So this is positive, right? And we know that we are not replacing for the actual value of delta kt plus 1, which means that this is just an approximation of what we have on the right-hand side. In this case, investment and the depreciation of capital times capital stock. And the other part of the derivation of the fundamental equation requires that I re-express everything in per capita terms. So to do that, I will be dividing both sides of the equality by population or labor. I remember that both are the same by assumption in this model. Which means that if I rewrite every element of this approximation, what we have is that kt over nt times delta kt plus 1 over kt. I hope you see the difference between my uppercase and my lowercase letters. This is approx. My investment divided by nt minus delta kt divided by nt. So I want to quickly explain two things. One is that obviously this is, again, the capital labor ratio, which is my lowercase kt. Same here. And same here, right? So that was easy to see. There is something that probably is not that easy to see, but another assumption that Solow made in his seminal paper is that investments are equal to savings in the economy. And savings, by definition, are a fraction of GDP. So what we have in this term that I highlighted in red is actually the savings rate times GDP, right? But since now I'm re-expressing this in per capita terms, it has to be the case that I will replace this for GDP per capita, which clearly we know that is determined by the production function, right? So that's the step that might be not super clear to see directly from here. If it wasn't, it would be probably easier to replace savings for investment. I mean, the other way around. Investment for savings in the previous steps, and then to re-express savings as a fraction of GDP, and then until this point, re-express GDP in per capita terms. No, nothing changes in the analysis. I will do it just for deductive purposes, but it doesn't really matter in what moment you see this. It should be by assumption, no, that you are making this. I will do it directly in this step. Sorry that I'm going back and forth, but I think this better improves the explanation. So if you replace not only subtract KT, but also replace investment for what we assume that investment is, in this case, savings, and that should be the step that you should get at that point. And in this third equation, you can also say, well, we know that savings are, in fact, just a fraction of GDP. But obviously, what you know is that GDP is determined by the production function, which means that a further simplification of savings should be something like savings rate times the production function. And now it should be clear, no, that the moment we divide by population, or in this case labor, we re-express the production function, the aggregate production function in per capita terms, and that's it. It's nothing weird. It's just that probably for you it will be easier to see the step by step, no, instead of just directly simplifying at the end. And it means that I'm gonna rewrite the simplified version of what we have so far, but you will see how many things simplify even further. So we said capital labor ratio multiplied by the growth rate of capital per worker plus n times capital per worker, approx savings rate, production function per worker, minus delta capital per worker. So here is where things get easier, and that's because you can get rid of the capital per worker on the left-hand side of this approximation. And the other thing that you can do is to subtract capital per worker on both sides of this equality. Sorry, not equality, approximation. Which means that on the left-hand side, you get rid of this NKT. And on the right-hand side, now I'm gonna rewrite it. What you will see is that left-hand side gives only the change in capital per worker, which is approximately the same as savings in the economy in per capita terms, minus, and you could re-express this as the population growth rate plus the depreciation rate times capital per worker, which is precisely what we wanted to show. This is the one that is known in the literature as the fundamental equation of the Solow model. So probably one of the things that you saw in your courses is that this equation tells you the relationship between savings and what you need, and how those savings compensate for the additional workers in the economy and the depreciation of capital. If they don't compensate and capital depreciates faster or population grows faster, then turns out that you are losing capital. But if savings grow faster than what you need to compensate for those additional workers and for the depreciation, then you will accumulate capital. And last thing that I'm going to mention is that obviously the other thing that you know is that in the steady state, it has to be the case that you don't accumulate capital, meaning that you exactly save what you need to compensate for those additional workers and for the depreciation of them. So that is true in the steady state, which basically means in the long run. Okay, so I hope the video was useful and see you next time.